Hello and welcome to this ICSR 20 paper presentation in the recommendation session. The paper is titled Automated Reuse Recommendation of Product Line Assets based on Natural Language Requirements. I am Mohammed Abbas and I work together with Mehrdad Saadatmand at the Research Institutes of Sweden, Eduard Enoiu and Daniel Sundmark. They work at Mehrdad University. And this work is done in collaboration with Bombardier Transportation. Claes Lindskog is leading the team on propulsion control software. The work is funded by the ETIA 3 Shift project. So to introduce the context a bit better, we need to see what kind of company we are working with. So Bombardier Transportation developed trains, and these trains could have different seat capacity and speed requirements. Type of power is another source of customization, and Bombardier tries to target all these different market segments with different products which could be customized to address specific customer needs and regional standards. At the same time, at the team, quick and quality delivery of these products is of very high interest. So to see real examples of these products, Bombardier is developing a very high-speed train for China, and then the trams that you see in France are also mostly developed by Bombardier. And then there are trains running on batteries in Germany. So there is a huge variability inside these products, and they could be customized for different customers. So at heart of all these systems is the propulsion control software responsible for power propulsion control. At the team, as I mentioned, quick and quality delivery is of very high interest. So one solution to this could be, since these products share a lot of commonalities, so we could exploit these common features using a software product line. But the product line engineering adoption could be very expensive, and the product line engineering process could vary from company to company to reduce cost. So there could be different approaches to the adoption. Big Bang adoption tries to drastically change the processes inside the company, while in contrast, there are other approaches to allow this transition in evolutionary and incremental manner. So companies often try to reduce the initial cost. If you look here, the single system development would cost very less initially, but when the number of derived product grows, this cost would become very high. While in contrast, if you look at the product line engineering process, it would result in a very high initial investment, but would reduce with time. So companies try to be somewhere in between and try to follow some evolutionary development of these product line assets. So in the studied setting, the software product line is realized by overloaded assets, and they are developed in evolutions. In the reuse process, the company is following is a clone-on way of reuse because it is quite quick and it requires very less initial investment. So when companies follow this evolutionary adoption of product line engineering process, this also results in evolutionary development of product line assets. This means that over the years you would develop a lot of products which would be reusing a lot of assets from the product line. But in some cases, these since they are following evolutionary development, these assets could be modified to address particular customer needs. This results in a lot of functional variants of the same asset coming from the product line. So when you have done a lot of these products and you are supposed to develop a new product, what assets could you reuse to realize the requirements of the new product? Because now you have a lot of functional variants and the original versions of the assets coming from the product line. So to tackle with these challenges, this resulted in a new process at the company for reuse analysis. So now when they get new customer requirements for a new product, mostly in natural language, some key engineers take some coffee and recall all the existing projects that they have done over the years. Also, they look into the functional variants of different assets in the standard product line and come up with candidate list of assets that they could reuse to realize those new requirements. So if we look into this process would become impractical when the number of derived products grows. In addition to this, it is also very time consuming and prone to human error. This is also very dependent on the experience of those key engineers. So automation of this process is of very high interest in the current context. So luckily in the studied context, the requirements could be traced to their implementation. So in this case, just to give an example, these two requirements are implemented by asset X. And if you have all these existing requirements, what you could do is you could derive rules for future reuse. So for instance, in this case, what we could do is whenever a specified and altitude is mentioned in a requirement, we could easily say that asset X is the candidate for reuse. But this kind of approach is not scalable to define these rules because the number of requirements would grow, and then you have to update these rules again and again. So one way could be to use natural language processing approaches such as word embeddings. So word embeddings are a set of feature learning approaches used to learn different features based on their frequencies and their co-occurrences inside the requirement text. One approach to this is the term frequency and inverse document frequency coming from the information retrieval area of research. This approach is based on the term frequencies and their inverse document frequency score. It could be combined with other dimensionality reduction approaches like principal component analysis to generate dense vectors out of the requirements. In addition to term frequency inverse document frequency or TF-IDF, there are other neural network based approaches like doc2vec and fasttext for extracting meaningful vectors out of the requirement text. So we consider all of these. There are other approaches like GloveL and Elmo2 that we do not consider. So the requirement text could be vectorized. So meaning that for each requirement we would compute a vector based on some learned features. For example, in this case, specified and altitude are the two learned features. It's just an example. In this case, for example, the term frequencies would end up as the values of the vector. And whenever we have a new requirement, we do the same. We extract a vector out of the text of the requirement based on the learned features. For example, we would look for the frequency of altitude and specified, and what we could do is we could compute the similarity between the existing vectors of the requirements, and based on that, we could recommend reuse of product line assets. So we did something similar, but with added things. We developed a tool called a VariabilityAware reuse analysis, or VARA, which takes in customer requirements and their links to product line assets or the software realizing it. We apply some pre-processing techniques. In pre-processing, we remove stop words from the requirements, the English stop words like the, shall, and kind of words like these. And then we apply lemmatization. And lemmatization, what we do is we try to root up the words to their lemmas. For example, like interface and interfacing are the same words in different form. And when we lemmatize it, the lemma is interface. So this helps us avoiding different interpretation of the same word. And then we apply some vectorization techniques like TF-IDF, doc2vec, and fasttext. We support all of these three approaches, and the end user can select one of them. And then we apply some vector reduction techniques like principal component analysis in case of TF-IDF to reduce those computed vectors. And then we cluster all the existing requirements in shape of vectors while still preserving their links to the product line assets. So whenever the company gets a new requirement, is that we apply pre-processing vectorization and vector reduction, and then we try to compute the suitable cluster for that particular requirement. And we just extract their nearest neighbor and the software they are reusing, and then we generate recommendation out of it. So just to give an example, if the input requirement was that the user should be able to add an item to a cart, what would happen is that we recommend assets for reuse. In this particular case, they are mostly simulating models, so we could say that you could reuse some model from some project with some confidence value. So to evaluate our approach in Bombardier transportation, we defined these four research questions. The first research question is focused on identifying the most suitable word embedding algorithm in the context of product line asset reuse recommendation. And since some of the neural network based approaches could require a lot of data for training, We also investigated if pre-trained models could be used in the context of a product line asset reuse recommendation. Then the research question 3 is focused on the execution time of the different pipelines. And finally, in the research question 4, we are after the perception of the engineers regarding the results that we obtained, and what are the potential benefits, drawbacks, and improvements that we could do to make the approach better. So we followed some procedure to do this. We took two projects of the company with their reuse links to the product line assets, and we randomly selected 25% of the data as a test set, and the rest of the data was used for training. Then we used different pipelines to compare the results. So we used a pipeline which was totally random. It was just recommending random assets for reuse. Then we used the term frequency and was document frequency based pipeline for reuse recommendation. Doc to Vec with training, and also a pre-trained model, and fast text, a model that we trained, and a model that was already trained on Wikipedia documents. This was to answer the first three research questions, and to answer research question 4, we drafted an instrument and conducted a focus group session with 5 engineers at the company, all with more than 10 years of experience in working in the propulsion control software domain. This session was transcribed, and on the transcript we applied thematic analysis to report the themes and sub-themes for in the results of research question 4. So moving on towards the results. So as mentioned, we considered different pipelines based on different word embedding algorithms. So term frequency and was document frequency was one of them, doc to vec, and a pre-trained version of doc to vec. We also considered a self-trained fast text and a pre-trained version of fast text model. And we compared all these pipelines based on two different metrics, accuracy and exact match ratio. So our recommendation is considered accurate if the ground truth is somewhere in the recommended list. A recommendation is considered an exact match if the ground truth is on top of the recommended list. So based on our results, term frequency and was document frequency based pipeline outperformed all other word embedding algorithms, both in terms of accuracy and exact match ratio. Also, the time taken for recommendation generation per requirement is comparatively quite low compared to other pipelines. Other pipelines also performed better in terms of time taken, but not in terms of accuracy and exact match ratio. To answer research question 4, we conducted the thematic analysis on the transcript of the focus group. So we predefined some themes, benefits, drawbacks, and improvements in the instrument of the focus group. We conducted thematic analysis on the transcript of the focus group to identify sub-themes relevant to these themes. So regarding the benefits of the approach, the engineers think that this approach could help in automation of product line assets reuse. The recommendations generated are quite relevant and useful for the engineers. The reuse analysis has become quicker with this tool compared to the manual way of working. However, the approach still has some drawbacks. For example, the approach is not documented well because it is a research prototype. The effective selection of the training set is also a bit of a problem for engineers because the quality of the recommendations is highly dependent on the quality of the training set. The tool is also not integrated into their development processes like their requirements management tool at the company. So they suggested some improvements that we could do to the tool. One of which was that beyond certain threshold of the similarity value, we should stop recommending reuse. And also there should be some way to exclude some cases from the training. To summarize, we proposed an approach for automated reuse recommendation of product line assets called VARA. This tool uses natural language processing and machine learning approaches to recommend reuse of product line assets. VARA reduced the time for recommending reuse to 270 seconds plus few days for manual review of the recommendations. We achieved around 74% accuracy of the best pipeline, which is based on the term frequency inverse document frequency. Engineers think that the results that VARA produced are insightful and useful in their use activities. In addition to this, VARA is also being used as a tool for evaluating risk of new projects at the company at the moment. In future, we are planning an empirical evaluation of a team using a recommender system and compare it with a team not using a recommender system in product derivation in context of software product line engineering. In addition, we also want to bring up this analysis to other levels of requirements to support project bids. We are also planning to extend the approach for requirement similarity based test selection and prioritization. Uh, it has been a really good collaboration with Bombardier, and we are planning future studies with them. Thank you so much for listening. If you have any questions, please feel free to ask.